Building a DSL towards higher level syntax or programming languages. The main goals of this experiment are that I want to write a program as a diagram, and I want to use whatever existing tools I can use to speed up my development of this. How can I do this? Well, I can draw the diagram using draw.io, and draw.io saves the diagram as XML text. Actually, it's GraphML. To take the text and parse it into a program, I can convert the XML to JSON. I might write a DSL to help with doing that. In fact, that's going to be the subject of this talk. And thirdly, I need to write a small program that inhales the JSON after it's been converted and then runs the whole DPL program. I'm just going to leave that alone for now and leave it elsewhere. What have we got and what's missing? Well, we already have draw.io off the shelf. We can download it from this location. It's in the bibliography too. If we're going to use a DSL, which I prefer because a DSL will allow me to write what I want done in a more concise manner and then convert it to something else. In this case, I'm going to convert it to a Python program. And the Python program is going to run the code that I wrote in the DSL, and it will convert the XML to JSON. We also need to write a small program that inhales the JSON and executes it. I'm probably going to do that in Python, and I probably won't show it in this little talk. So now we have a sub-goal, the number 2 sub-goal of this earlier thing, which was creating a DSL. So we're going to write a DSL to convert XML to JSON. That's the subject of this article. And the real interesting part is, how can we do this quickly? How can we do this in a couple of hours instead of days, weeks, or years? How do you write a DSL quickly? Well, you use existing technology as much as possible. I've collected up OMJS. OMJS is based on parsing expression grammars, pegs, and I built a little extension to OMJS that I call T2T, which means text-to-text transpiler. I divide and conquer the problem. The actual XML that's saved by draw.io for a simple diagram can be huge. It will defeat any tool that tries to build an in-memory AST. So we need to write something that will cull the XML down to the bare essentials so that then we can use something more interesting like OMJS that builds ASTs. So a sub-goal of this sub-goal is to create a DSL that will do stream parsing instead of full-blown AST-based parsing. We'll use that to cull the XML. Once we get the XML down in size to where OMJS can ingest it and produce a full-blown AST, we'll use OMJS and T2T to do the rest of the work. I'm going to use the little extension to OMJS that I've created called T2T. It uses the OMJS grammar for the AST, and it uses another little DSL tool that I call RWR for rewriting after OMJS does a successful parse. To do this stream parsing, I've decided that I want to do recursive descent parsing. I don't want to build an AST as we go. I know that means I can't do any rewinding. I can't walk up and down the AST. So I have to do things immediately as I parse them. The syntax I'm going to use is inspired by an older tool that I remember learning, which is called SSL, Syntax Semantic Language, that was built for writing recursive descent parsers for larger projects like full-blown compilers. I'm going to use Python as my assembler. Actually, any target language would do, but I happen to know Python better than I know Rust, so I'm just going to use Python to make my life easier. You can substitute whatever language you want in the stuff that follows. I believe there are about 20-ish operations to do the parsing part. There's about 1 operation for declaring errors as we go. There's about 1 operation for calling other rules written in the stream parsing DSL, and there are no operations for implementing actions. I'm going to punt all the actions to canned library code if I need any of them. I've got it down to a handful of actions that are built into the structure of the DSL. In general, though, SSL allows one kind of action called a mechanism that you can express in the DSL, but you can't express how to implement it in the DSL. The implementation is done in whatever support language gets used with the SSL DSL mechanisms. In the cases that I looked at, it was PT Pascal and concurrent Euclid and stuff like that, C. But we don't need that here, so we're not going to do that at all. What's the model for the stream parser that I'm using? I'm going to use T to T to do the grammar parsing, and the part of T to T that helps me rewrite things in a more succinct manner than writing the same stuff in, say, JavaScript. I'm going to generate Python code. The generated Python code will be a stream parser that stream parses stood in. It's going to be a standalone Python program when I'm done. I'm going to use T to T to express the stream parser in a succinct way, but then use T to T to take that succinct expression, turn it into a less succinct Python lump of code, and then I'm going to emit the Python code as text, and then run the Python compiler interpreter on it to actually run the stream parse. To build the stream parser, I'm going to use a model of a small machine. And the machine is going to have several stacks and an object, which I'm calling a character stream. There's going to be a stack for the current rule name. I'm calling that breadcrumbs. Basically, you can follow where you got to and where you're going. There's a working stack, so every rule in the DSL will begin by creating an empty string, and then all the pattern matches and actions within the rule will build up that string. And when the rule is done, that built-up string will be returned to whatever other rule called it, or to the very top level. To help with returning things, I'm going to have a return stack. It's really just a stack of strings. All of these things are pretty obvious in Python. They're just stacks, arrays of strings. To do rule calling, I'm just going to use Python functions and use its call stack. And I'm going to build a class, at least one class, called a character stream. And it's going to have a cache of characters and a position, and then a handful of method calls: get, see, rewind, clear, accept the current set of characters. So this thing's going to build up a string of characters that it likes. When it says I've got everything I wanted to match up to this point, it will accept them, which means it'll put them somewhere, clear out the cache, back to an empty string, and then move on. And then there's a bunch of miscellaneous methods. The parser itself will have a bunch of operations. They're kind of like opcodes for this mini machine that I'm building. So it's push new string, return the string, and pop the working stack. Ignore the string that we just built, pop it off and throw it away, start a breadcrumb, memorize the name of the current parsing rule. In the rule, tracing, calling, appending things to the cache, accepting things that are in the cache, peeking, looking ahead to see if all the characters I want are lined up in the cache already or are next in the input stream. Have we reached the end of file? After we call a rule and it returns a built-up string, we want to take the built-up string that it returned and append it to the string that we're building up. So append return string, we'll do that. Need is basically just a parsing function that says we better see one of these characters or this string next, or else we declare a syntax error. There's need and append, which is basically the same. It says, look for this string, and if you find it, append it to the current working buffer and clear the working buffer. maybe append says, try to see if you have the next set of characters. If so, accept them and append them to the working buffer. If not, rewind and continue on. Declare a syntax error and a bunch of other miscellaneous stuff. Let's look at one of the rules and what it looks like when done in Python. So here is what I think is a more succinct expression of what I want to parse. The rule is called XML, and the rule itself says look for spaces, then look for a less than sign, then call the rule name, call the rule attributes, and then you've got a choice. If you see a greater than sign, call the content rule, then look for a less than slash, then call the stuff rule, and then look for a greater than. The other option is look for a slash greater than. If you see one of those, accept it and do nothing else, then fall through. I've marked up the syntax of the rule. So defining the rule XML is colon, space, and the name of the rule. Caret equals says define the rule to return its result. Don't bother manipulating it any further. Other rules have an at equals that call a manipulator function later in the DSL. The first line of the rule does a call, then a must see, then a call, then another call, as I've shown with the red ellipses and circles. After that first line, there's a choice, an input choice, and it says either look for a greater than or a slash greater than. And then if we see a greater than, do this stuff, content, look for less than, slash, call stuff, look for a greater than. And here's the Python that comes out of that. As you can see, there's a lot more Python, and if I had to write this by hand, I would be too mired in dealing with all the little niggly details of writing the Python code. I'd probably want to try and optimize some of the Python code, which would slow down my thinking. We can see there's basically a one-to-one mapping from this syntax to what comes out in Python. So I'm using Python kind of as an assembler, and the 20-ish operations, I know that I can use those and I can emit them. The first blob of instructions emitted by the DSL are just to define a Python rule or a function in Python that takes one parameter _r, I decided to call it. It creates an empty string and it pushes the name of the current rule XML onto the breadcrumb stack. After that, we call spaces, and when spaces returns, we pull the return string off of the return stack and append it to our working string. Then there's need and append and call name with appending return, call attributes, append and return, and then the choice, which I've decided to write this way in Python. It looks kind of goofy Python, but when you're generating code, the difference between how to write the if part is different than the edge cases of writing elifs. I decided for whatever reason, just to make my life easier, that I would make the choices all elifs. And the first part I just punt and say it's always false, and we'll let the Python compiler deal with a false if. It should optimize that away if it's any good. I don't really care, because this only has to run fast enough on my decent development machine, a laptop running Mac OS. And at the very end, we clean up the breadcrumb stack, we pop off the XML, do anything else that's necessary, and then we pop off the return, the working string, we pop it off the working stack, push it onto the return stack, and then we return. So what have we learned about quick development? Cheat as much as possible. There was a bug earlier that I mentioned here in the green part. The green part should actually produce code that fails if none of the elifs fire. And I didn't do that. It didn't really matter for this project. And if this is a one-off, who cares, right? Knock it off, throw the code away, or leave it lying around for whoever wants to maintain it. If someone wants to steal this DSL and use it in another project, will they get problems? That's the only question. But again, the attitude is we don't write generalized code, we write specialized code on a per project basis. And if you borrow the code for another project, you know that it may or may not suit what you need to do exactly, and you need to look more carefully. The final point is that I use something that I'm calling failure-driven development, which is the idea that I write code that writes code instead of writing code by hand, so that I'm free to iterate on the design and throw away everything I've done and just push a button and regenerate all the code again. And that's what I'm doing here. I've made the design more succinct than if I had used a general purpose programming language. That's the DSL, the stream parsing DSL. I've said clearly what I wanted to do without judgment on how to do it. And then I wrote the code to convert that succinct expression into a general purpose programming language that I use as an assembler with a handful of instructions that I know that I can use.